So we have intersymbol interference or ISI because of low pass behavior of the channel. That is not the only thing that gives intersymbol interference, but we'll see the other types later. But primarily this is what happens. In many channels, they are either too long wires or they have too much capacitance or something. So they are not able to hold the magnitude response at high frequencies as well as they do at low frequencies. So there is significant high frequency attenuation. We took the example of a low pass filter and saw that first order RC low pass filter and saw that if the bandwidth of the filter is about a third of the data rate, it's okay, but below that you can start getting significant ISI. Let's say we have this RC, the response is something like this, and this is the minus 3 dB point. If I had a series inductance, what do you expect will happen? I'll have a peak at 1 over root 2 pi LC. Will the bandwidth be smaller or larger than this? I mean, will it do something like this? Will it do something like this? Basically, is the response going to get more broadband or less broadband? So what happens is, if you, let's say this is the response of the RC filter. For very small values of inductances, not much happens. It may have some changes here and so on. And then you can always find a value of inductance where it does this. It becomes a second order Butterworth filter. And if you increase the inductance beyond that, what I believe will happen is it will start peaking as well as the bandwidth will reduce. Because you have here the variable is L. So as you keep changing L, this is what will happen. So this is a series LCR network. The Q being 1 over R square root L by C. As L keeps increasing, the Q keeps increasing. But also the natural frequency being 1 over square root LC, the natural frequency keeps falling. So this is what you will see. But you can, there is one value of inductance where you can adjust, where you can get the maximally flat response or the Butterworth response. And you do use the trick in some cases to extend the bandwidth of RC. And this is a well-known thing. In fact, a long time ago, this fellow, have you heard of this guy? A very old physicist. So, loading coil. So you have a long line, and actually the puzzling thing firstly was that the delay seemed to be varying as the square root of the length of the line. Square of the length of the line. So there is, what is puzzling about it? The delay of a wire was proportional to L square. What is wrong with this? I mean, is that something wrong? Anyway, this was true. This was what was measured. But what was puzzling was, if you look at delay per unit length, for every meter of wire, delay by L, that itself is dependent on L. So it appeared as though the delay that is offered by every length of the cable dependent on the total length. But how does the cable know that the rest of the cable is connected to it? That's a little weird, right? So, but it comes out of diffusion equation, and this is the right thing. So, anyway, what this guy figured was he split it into sections. So this is a cable, and then you put these coils in series, and it actually made the transmission much better. Anyway, that also initially was not observed, that you put inductance and then it makes it better. But then it does make it better because of effects like this. So it becomes more like a LC transmission line, right? The uniform, the lossless. There is loss in this, but there the delay is L, and also the attenuation is much smaller. It does work like that. Of course, there is a certain value of L which works. If you increase it beyond that, it won't work. Bandwidth of the channel, if it is greater than some alpha Fs, where alpha is a fraction, things seem to be fine. You don't have significant intersymbol interference. This again is the intuition we got from first order RC circuits, but it turns out to be generally true. Again, the same thing holds true when you make circuits for, let's say, 10 gigabits per second or something. What should be the bandwidth of your circuit? And the rule of thumb that is used is if the bandwidth is greater than 75% of Fs, you don't have significant deterioration in the signal. That is, you don't have significant intersymbol interference. So, if we represent the impulse response of the channel, impulse response of the channel plus transmitter, if this is the case, the maximum ISI that you can get is summation of absolute values of H for n not equal to 0. N equal to 0 is assumed to be the peak value of the cursor. If you sum all the other elements, they can all add in a destructive fashion to your signal. So, if you send a positive symbol, then you can subtract this from H of 0 and get the resulting value. And that is the worst case signal that you get. So, the result of this is that this is clearly smaller than H of 0 itself. And if you add any, let's say, Gaussian noise to it, the bitter rate will be much greater in this case than in this case, when you didn't have any intersymbol interference. The other point to note is H of 0 itself is smaller than 1, right? As we saw, as the bandwidth of the channels decrease, again this turns out to be true in general. So maybe for more or less ideal RC filter, high bandwidth RC filter, the response looks like this. But as you reduce the bandwidth, the main cursor reduces, and the post cursors increase. So h of 0 itself is smaller than what it could be, and the other elements are larger than what they will be in the ideal case. Okay, so that can severely degrade the bit error rate. And of course, if this happens to be h of 0 minus the summation of magnitudes happens to be less than 0, then you don't have any, even in absence of noise, you will get bit errors. So ISI can cause bit errors, and this entire thing can be plotted. So h of 0 is here, and h of 0 plus this summation is here, and h of 0 minus this summation is here. Now, the signal can occupy any of these, the signal will be somewhere between this point and this point, depending on the input bit pattern and how many non-zero elements in the ISI you have and their values and so on. And this part is the part where you don't have any signal, and that is known as eye opening. I have not defined what an eye is. In fact, this is not the picture that we use. We can use a more vivid picture in continuous time to visually gauge how good the signal is, right, in presence of ISI, and that's known as the eye diagram. So, but at least here it is clear that this part, which is the opening, determines how much the bit error rate is. The eye diagram is, it's more graphically intuitive. What it is the same thing, but in continuous time. You don't look at the values of the samples, you just look at the value of the entire waveform. So, let's say you have a signal like this, you have a system like this. The output signal can be something on this side. You just look at this waveform, it's hard to say. You have to go and measure where it is minimum and so on. So, what is usually done is, you take 2 periods of the signal, that is 2 bits, 2 symbol durations, and plot it. I'll plot it on an enlarged scale, and then you take the next 2 and plot it on the same axis, and you take the next 2 and you can do and then it also has things like this where the bits are not varying. Is this clear? I just take some n periods. In this case, I have taken 2. I take 2 periods of the signal and successive 2 period intervals and overlap all of them onto a single diagram. What is the use of this? So, firstly, if you go through all the possible bit patterns, then this kind of shows you the transitions and the y-axis values for all the possible bit patterns. And also, essentially, this part that we have here is nothing but, if the sampling instant is this, what we see here. Basically, this is just a collection of all possible y-axis values when we sample it. Now, this eye diagram is for continuous time. Let's say the sampling instant is here, then I can look at the thickness of this and determine how much the ISI is. So, I overlap the successive 2-bit intervals onto a single diagram. So, let's say my sampling instant was here. So, in the first case, I will get this. In the second case, I will get this value. Third one, I will get. So, in the diagram, all of them will be on top of each other. Okay, rather this and the successive 2-bit things will be on top of each other. So, this will be here. The next one will be here. The next will be here, and so on. So, essentially, and the h of 0, these values that I wrote here are nothing but the sampled values that you can see by looking at where the sampling instant is on the eye diagram. So, essentially, I want to see how spread these values are. Okay. Ideally, they should be this should be 1 and this should be -1. If I had an ideal rectangular data, my eye diagram would look like 2 boxes, because basically this is all possible 2-bit transitions. I am drawing an eye diagram with 2-bit, which is 2-bit wide. I mean, it can be any number of bits wide. So, in this case, you can have 0, 0, 0, 1, 1, 0, and 1, 1. Okay. So, that's all that is there. In this case, there is no ISI at all. So, you don't have to look at like longer bit patterns. So, this is what it looks like. And then, anywhere you sample, so let's say this is the sampling point. So, that corresponds to this here. Okay. This and this. So, I look at the values at the sampling instant, and the spread of that tells me the ISI. So, the values that I get here are, this is just from the definition of h of n. H of n is simply when I sample the output at with this particular phase, and that's what I am doing on the eye diagram. So, of course, for a rectangular data with no ISI, the eye diagram is quite boring. But if you have an RC filter, then it can look something like this. So, it will have all possible transitions. And also, if you have a further lower bandwidth RC filter, it may not reach the full value. In that case, you can get something like this, or you can get something here. Something here. So, this will become very clear once you plot a few of these cases. So, this is typically what it looks like. And if I look here, there will be some area in the middle where there will be no transitions, no traversal of the signal. And that part is the eye opening. And that, if this is the sampling phase, then the values that you see on the y-axis correspond to these values. At least this is the range of values that you will see. And you typically draw the eye diagram for a 2-bit interval, because at least then you don't know the timing of the signal. You cannot draw it arbitrarily. There will be one full eye. This looks like an eye. That's why it's called an eye diagram. There is some opening in the middle. So would you want the opening to be wide or narrow? It should be as wide as possible so that you can detect the data without any error. So the vertical eye opening gives you a measure of bit error rate. If you add a given amount of noise, the vertical eye opening gives you the signal strength. So normally in a case like this, when you don't have any ISI, the transmitted strength is the signal strength. But if you have ISI, you may be transmitting a large signal, but the ISI can also be large. So it is the net that counts. Okay. So signal minus the ISI divided by the sigma of the random noise will determine the bit error rate. So then I can also point out that the horizontal opening of the eye is also of some importance. Is also great importance in fact. Why is that? What about it? So there are two reasons why you can get errors here. So let's say you have a clock that is sampling that's supposed to be sampling in the middle of the data. Okay. And let's say it's sampling on the rising edge of the clock, and I'm drawing a sinusoidal clock. So these are the sampling instants. So there are two reasons for error. One is when you sample, some noise can be added to it. So let's say it's Gaussian noise. It will have a distribution like this, and the area under the zero line gives you error. Right? Basically, I'm saying if you add this value to the noise distribution, then the noise distribution will be shifted around this value. And if the noise will pull you, if the noise pulls you to negative values, you have a bit error. That is one possibility. What else is possible? The clock, it turns out, can have noise, right? So normally you want the clock to be perfectly periodic, but in reality it turns out to have some extra stuff, phi of t, which also can be like noise. And that noise, and this also is modeled with a Gaussian noise. So this edge, instead of being here, can be shifted to other values with certain probability, and that probability depends on the variance of this phi. Okay, where do you get zero crossings of this? When this entire argument is integer multiples of 2 pi, right? Integer multiples of, sorry, if it's cos, it is whatever, n times pi plus pi by 2 or something. But anyway, I'll just say integer multiples of pi, and that can be shifted around because of noise. It's not when, and this will be equal to n by f naught if there is no noise. If there is noise, then it won't be at 1 over f naught, okay, 2 over f naught and so on. It will be at some other, it can be at some other points. So there is a distribution for that also. So it can sample here with a high probability, but there is some probability that it will sample somewhere in the wrong bit interval. So because of jitter, the clock edge will move around, and it can be shifted so much that it is sampling in the previous bit or the next bit. That is entirely possible. How? The probability of that depends on the variance of noise. Now if it samples in the wrong bit, not the current bit but either the previous bit or the next bit, and let's say the data is completely random, there is a probability of half that bit is in error. Because you could be sampling the previous bit could be coincidentally the same as the current bit, in which case you don't have an error, or it could be the opposite bit, in which case you do have an error. So depending on the probability that the clock edge moves to the wrong bit and the statistics of data, which we'll assume to be random now, you can have an error. So there is X moment because of the clock and Y moment because of additive noise. Okay? There is X moment because of clock jitter and Y moment because of additive noise. If you have an eye diagram, so eye diagram typically looks like this. Again, if you plot it for a couple of cases, it becomes very obvious why it looks. So this is some typical eye diagram that you may see. So this is nothing but a collection of all possible transitions. You can, if a 0 to 1 transition can go like this or like this, depending on what came before it and after it. So if you have significant ISI, you will have significant spread in the eye diagram. Okay? Because the transition from 0 to 1, if you have no ISI, is independent of anything. I mean, it is always this. But if you have ISI, it can depend on the previous bits and the following bits and so on. So you have something like this, and this is the vertical eye opening, and this is the horizontal eye opening. So as you see more and more, you see that this eye diagram is extremely useful because visually you can judge the quality of the signal. If you just give the waveform, it's very hard to do that, but with the eye diagram you can do. And also, typically the signals, in broadband communication systems, the signal quality is specified as eye diagrams. You need to have a certain opening in the y direction and certain opening in the x direction. So you have additive noise. This is like displacement in y direction, and this can give you bit errors, and you can have jitter in the sampling clock. This is basically displacement in x, and this can also give you. So this is the eye diagram, one period of the eye diagram. One period goes from here to here. So it always looks like this, and the eye diagram is periodic because in every part you include all possible bit patterns. Okay, the data is not periodic, but you have random data, and then you take 2 bit intervals and then overlap them. So the eye diagram itself is periodic. Is that convincing? Because you take all possible bit patterns for every period here, right? If you take an eye diagram from a long enough bit sequence, you will have a periodic eye diagram. Think about it. If it's not convincing, I can explain it further. So this is what the eye diagram looks like, and this is the vertical eye opening. This is the horizontal eye opening, and this part, the part on the x-axis that is covered by transitions, is known as jitter. Okay, this is the jitter in the data, it's not the same thing that I described here. This is the jitter in the sampling clock. Sampling clock can move back and forth. This is the jitter in the data. So if you have an ideal rectangular pulse, then the zero crossings will always be at some integer multiple of ts. So maybe there are some transitions missing, but if there are transitions, there will always be at integer multiples of ts. But if you have intersymbol interference, this may not be true, because clearly for an RC case you can see, let's say you have a low bandwidth RC filter, then let's say it starts from this value, the high value, then it doesn't have time to go all the way low, and then it comes back here. So you can calculate this part. This part will be much less than, the spacing between this and this will be less than the bit interval. And in fact, the less the bandwidth of the RC, the smaller this interval is. Is it okay or not? I don't know if everything is being understood or nothing is being understood. What is the spacing here or here in the above diagram? So it can be less than ts. That's all I'm saying. Okay. So for instance, let's say I have a single isolated pulse, right? It's always, the input is always -1, then it goes to +1 and comes down. The output, if the bandwidth of the RC is large, it will do this. Then this and this are more or less separated by ts. Then as the bandwidth reduces, it can do something like this, where the spacing is much smaller than ts, because it doesn't rise to high enough values. And if the signal stays negative throughout, then the eye diagram is closed, meaning you will never have this opening. If for a negative input, the output doesn't go negative, the eye diagram is closed. Okay. So this is known as the eye opening. So you can specify it in the positive and you can specify it on the y-axis and the x-axis. The reason this is useful is just by looking at it, you can judge how much the bit error rate is. Okay. So if you know how much noise is being added from this y value, you know how much the bit error rate is because of that. And if you know how much jitter the clock has from this opening, you know how much the bit error rate is. Is it clear? And this part, the part of the x-axis that is closed, is known as the jitter in the data. So if you had an ideal eye diagram, the transitions would be here, and the spread in the x-axis would be 0. That is what the jitter is. It's basically the spread. All the zero crossings should be at integer multiples of the symbol interval ts, but they will be at some delta away from ts, where delta being both positive and negative. The spread in the delta is the jitter. So all these have significant effects on the recovered data itself, and also you are supposed to recover the clock from the data. Now clearly, without knowing anything, you can still imagine that it's easier if the data itself has very well defined edges at integer multiples of ts. Then you can derive a nice periodic clock from it. If the data edges are jittering all around, if the zero crossings of the data are not at integer multiples of ts, it gets harder to determine what ts is. So we'll see the effect of this once we come to CDR circuits, clock and data recovery. Well, yeah, that's true. Here I'm looking only at the receiver clock. So the way you generate the data, there are many things that could contribute to jitter. Maybe the clock that you use to generate the data, that is jitter. The intersymbol interference as it goes through the channel, that is jitter. So jitter is like noise in that everywhere you will have it. Everywhere it will be present. Maybe it is present to smaller or larger extents, but there is no jitter-free clock, just like there is no noise-free signal. So this is an ideal rectangle, although it doesn't look like that. And let's say we want to calculate the response of this, response to the signal of an RC circuit of some bandwidth. And we'll say that it has an initial condition of -1, and then it tries to go up and comes back to -1. What is this time? This is -1 and +1. So from this edge, what is this? No, it's not 90%. It's the zero crossing of the data. Yeah, it is going to half the amplitude, so that is 0.69 RC. Okay, so this curve is described by -1 e to the -t by RC plus, and this has to be equal to 0. So e to the -t by RC is half. So t is RC log 2. So the zero crossing here is displaced from the zero crossing at the input by some amount. That is okay. That itself is okay. If all the zero crossings are shifted by the same amount, that is fine. That won't make any difference. Now what about this? Will it be shifted by the same amount or a different amount? This delta. Will it be the same as this or different? Why is it different? The initial condition is different. What is the initial condition? So you just put Ts here and you find the initial condition. Okay. So the initial condition is different. So this will be smaller or larger? Smaller. Okay. So this, if this is T1, this is T2. Okay. And this interval is Ts. So this interval is definitely less than Ts. Let's say Ta and Tb. Okay. Tb minus Ta is Ts. And T1 minus Ta is RC ln 2. T2 minus Tb is less than RC ln 2. So from this, can I say that T2 minus T1 is less than Ts? Or I can do that. Right? All I am saying is I have at the input I have two things separated by Ts. At the output I have the first one is separated by RC ln 2. And the second one is separated by something less than RC ln 2. So if this is Ts, this has to be smaller than Ts. Okay. What does it mean? That means that in the I diagram, you will see something like this. This is the zero line. So some transition like this will be part of the I diagram, where this is smaller than Ts. How much smaller than Ts it is depends on the value of RC and Ts. Okay, that is the time constant of the filter relative to the bit period. So, okay, I think I have just introduced some terminology without showing where we will use it, but at least qualitatively it is clear that horizontal eye opening is important for errors from jitter and vertical eye opening for errors from noise. Oh, okay. So we can discuss that if you want. So I was going to discuss equalization, but yeah, what was the I diagram is still the same thing. You take some integer number of symbol intervals and then plot it. So let's say the input is a 4-level signal, maybe -3 half, -half, half, 3 halves. I think I should make an animation with MATLAB or something and show it. That will become much clearer. But so the signal can be something like this. There can be transitions from everything to everything else, and so on. Right? This is the symbol interval Ts. In each Ts, it can be one of these 4 values. What will the I diagram look like if it's an ideal rectangular? So it will simply have this 3 boxes, right? Okay, this is what it will look like, because all the transitions will be at some at Ts. So if I draw it to 2 intervals, it will look something like this. Now let's say the same data was going through an RC filter. What would it look like? Yeah, there will be some rising exponential. So let's say the exponential does settle, but there is some rising part that is visible. Okay, let's say it's something like this. So in this, so there can be transition from this, similarly from this to this. So it's a collection of all possible bit transitions, And in this case, I said it fully settles, so I conveniently bypass the effect of ISI. Okay. I mean, there is some ISI, but not too much of it. Okay. So now, from the opening of each of these boxes, I can figure out. See, where will I put the thresholds for detecting data like this? Here, here, and here. So I'll always put the threshold between the two possible data values, right? So that's what I'll do here. So that is the opening that I'm interested in. Opening just says how far it is from the threshold, because I'm assuming that I'll put the threshold in the middle. So the opening is simply twice the distance, twice the distance between the threshold and each of the symbols. Okay. So this opening here, this will tell me something, and also this horizontal opening will tell me something. So it can look more and more attractive as you increase the number of symbols. So this is the eye diagram. It's very easy to generate. Once you learn how to interpret it, it's also very useful. And this is the standard way of specifying the quality of the received signal. And it's pretty clear because the eye diagram itself is periodic. It's very easy to, very intuitive and easy to look at. Okay. If I just look at the signal, then I have to see, what pattern it is and is this really the worst case or not. If I look at the eye diagram, I already know what the worst case is. Worst case of Intersymbol interference or jitter. See, there is no noise included in this. This is only because of Intersymbol interference and so on. So it only, in our particular case, let's say we have an ideal transmitter with perfectly rectangular edges with zero rise time, and that goes through an RC filter. So in this case, both the horizontal and vertical opening depend only on the RC values, okay, the time constant and the input period Ts. So you look at the part that is open and you know how much noise is being added, hopefully. And from the amplitude of the open part and the variance of the noise, you can judge the bit error rate. Okay. At least some case of worst case bit error rate. I don't think that's the case. Why did you say that? That will not be the case at all, because if you have intersymbol interference, the initial condition matters, right? Maybe going from here to here is the worst case, isn't it? For the horizontal eye opening, let's say I start from here and then I go to this, or I go to the next level, or I go to the next one. So it could be that, and if I put the threshold at some point, let's say the threshold is here and here. So the threshold here could be larger, here could be smaller than that, and here could be the smallest. So that's possible. So it's not that the smallest one matters. Because you have 4 levels, you can have some wide combination, very like large combination of initial conditions and the final values. See, what is the ISI in this case? So we had binary data, we got the ISI to be summation of h of n for n not equal to 0. What is the worst case ISI in the 4 level case? Okay, let's say I want to receive this symbol, okay, plus half. How would you construct a signal that has worst case ISI given the impulse response of the channel? You will give all of them the maximum weight with the opposite sign, right? You will make sure that in the convolution there is one that is weighting the signal and all the other terms weighting other parts. So you just make sure that the weightage for the other parts is more. Okay. So in fact that doesn't correspond to the middle transition, right? Because I would make sure that everything that is causing intersymbol interference is either plus 3 halves or minus 3 halves. So I'll have all these transitions and this one, that gives me the worst case. I have h of 0 plus h of 1, x of minus 1 and so on, all of the post-cursor terms, and h of minus 1, x of 1 and so on, all of the precursor terms. This is what I am interested in receiving. To see the worst case effect on this, I'll make sure that all of these have their maximum possible magnitude and the opposite sign to h of 0. Of course, this is h of 0, x of 0. So it has the maximum possible magnitude and opposite sign to h and h of 0, x of 0. And if, let's say this x of 0 is half, and I have to weight all of this by 3 halves to get the worst case weighting. And whether it's plus 3 half or minus 3 half depends on the sign of h. Think about it. If it's not clear, we can discuss it again. So, but it's not true that transition between half and minus half gives you the worst case. How will we analyze this? The eye diagram is not dependent on the receiver clock. What I'm assuming is this is the eye diagram of the signal before sampling. All of the eye diagrams are plotted up. So I have the sampling block here, and the eye diagram is plotted at this point. So let's say it looks something like this. So this is the part, and this is the open part. Okay, the part inside this. Now, if you have a certain jitter in the clock, let's say you have some added noise, and you also have jitter in the clock. So you are supposed to, you would normally want to sample here, hopefully. There is some optimum place, right? So if you go too far here, both the Y opening is reduced and the probability of going off to this side is increased. So let's say you have some sampling instant, and I'll call this the sampling instant. The probability of error is the noise taking you from here to something less than 0, or the jitter taking you from this point to something beyond this or something beyond this. So it's a joint distribution between the noise and the clock jitter. Okay. So basically the sampling instant, let me call this T0. The sampling instant is T0 plus Tj, where this is the jitter, and this is given by some, it's a normal distribution of with a standard deviation of sigma j, and the vertical part is whatever this I opening is. I'll call this Vi plus n, and this is some normal distribution with a standard deviation of 0 and Vn. You want to calculate the probability of T0 plus Tj going greater than, let's say this is T2, this is T1, becoming greater than T2 or less than T1. Either this will give you an error, or it's not or actually, because when the clock moves, you also have to look at the value of I opening at that point, okay, and that becoming negative. Okay. It's hard to describe verbally, but hopefully you got the idea of what's going on. So if I am sampling here, I can move the sampling edge because of jitter, and if I have moved it to this point, then the signal amplitude is smaller, so it can go down more easily with the same amount of noise. So there is some distribution of two variables, both the jitter and the noise that is added to the I. Okay, so that gives you the bit error. So the received clock jitter is not included in this I diagram. So far, the I diagram that I have been plotting is before you add the noise and before you sample the signal at the receiver.